Critical value approach to hypothesis testing. Criterion for deciding whether to reject the null hypothesis. We will always set up a normal distribution where we will label our z-score, our area, and the distinction between do not reject h sub 0 again, and the distinction between reject h sub 0 and do not reject h sub 0 again, and do not reject h sub 0. With the critical value, we'll find our critical value and decide whether to reject or do not reject h sub 0. Rejection region, non-rejection region, and critical values. Rejection region, the set of values for the test statistic that leads to rejection of the null hypothesis. If our critical value happens to be negative 1.645, then our rejection region would be all of the values for z that are smaller than negative 1.645, such as negative 2, negative 3.05. Non-rejection region, the set of values for the test statistic that leads to non-rejection of the null hypothesis. If our z-value was negative 1.645, the non-rejection region would be the values larger than negative 1.645, such as negative 1.7, again, such as negative 1.6, 0, 2.5, and so on. Erase the and so on. Critical value, the value or values of the test statistic that separate the rejection and non-rejection regions. A critical value is considered part of the rejection region. For this illustration, our critical value is negative 1.645. For each problem, we will set up our rejection region, critical value, and non-rejection region. Graphical display of rejection regions for two-tailed, left-tailed, and right-tailed test. Starting with the two-tailed test, we would have a critical value in two spots, a positive and a negative value. The rejection region would be any values to the left of our smaller value or to the right of our larger value. Our do not reject region would be between the two values. Left-tailed test. Our critical value is usually to the left of 0. Our rejection region would be all of the values less than 0, again, less than our critical value, and our do not reject region would be all the values greater than our critical value. Right-tailed test. We would have our critical value, which is usually to the right of 0. Our rejection region would be all the values greater than our critical value to its right. And our do not reject region would be all the values to the left of our critical value or less than. Or again, to the left of our critical value or z-values that are smaller than our critical value. For a two-tailed test, the sign in HA will be not equal to, and the rejection region would be on both sides. For a left-tailed test, the sign in HA would be less than, and the rejection region would be the left side. For a right-tailed test, the sign in HA would be greater than, and the rejection region would be the right side. Obtaining critical values. Suppose that a hypothesis test is to be performed at the significance level alpha. Then the critical value or values must be chosen so that if the null hypothesis is true, the probability is alpha that the test statistic will fall in the rejection region. The test statistic for a one-mean z-test is z equals the sample mean minus mu sub 0, equals x bar minus mu sub 0 divided by sigma divided by the square root of n. Critical values for a one-mean z-test at the significance level alpha if the test is two-tailed. For a two-tailed test, we would take our value for alpha, divide it in half, and that would give us the area to the left of our lower z-score and to the right of our higher z-score. Our do not reject region would be between the two z-scores. Critical value for a one-mean z-test at the significance level alpha if the test is left-tailed. For a left-tailed test, we are given alpha. We find our negative z-score. Our rejection region is to the left of that critical value, and do not reject is to the right. Critical value for a critical value for a one-mean z-test at the significance level alpha if the test is right-tailed. When we are given alpha, we find our positive value for z sub alpha, and then our rejection region would be the z-values to the right of our critical value, and our do not reject would be the z-values to the left of our critical value. Steps in the critical value approach to hypothesis testing. Step 1. State the null and alternative hypothesis. Step 2. Decide on the significance level alpha. Step 3. Compute the value of the test statistic. Step 4. Determine the critical values. Step 5. If the value of the test statistic falls in the rejection region, reject H sub 0. Otherwise, do not reject H sub 0. Step 6. Interpret the results of the hypothesis test. Example. The graph below portrays the decision criterion for a hypothesis test for a population mean mu. The null hypothesis for the test is H sub 0 colon mu equal mu sub 0. Assume, again, the curve in the graph is the normal curve for the test statistic under the assumption that the null hypothesis is true. So in our picture, we have a value for z that is 1.881, and we have an area to the right that is 0.03. Determine the rejection region. Since our z-value is 1.881, and since it is shaded to the right, we have a right-tailed test, so z is greater than or equal to 1.81, again, 1.881. Determine the non-rejection region. Since the rejection region is to the right, the non-rejection region would be to the left. Z is less than 1.881. Continuing our example, determine the critical value or values. Since they give us the z-score of 1.881, and that is the cutoff point between, again, and that is the point that determines the rejection region versus the non-rejection region, our critical value is z equals 1.881. Determine the significance level. Since the area to the right of 1.811 is 0.03, alpha equals 0.03. Construct a graph that depicts your results. So we have our normal distribution with the z-score of 1.881 marked and an area of 0.03 marked. So to construct constructing the graph that depicts your results, we want to mark what is our critical value, which is the 1.881. Then we want to make sure we mark the rejection region, which is to the right of 1.881, and the non-rejection region, which is to the left of 1.881. Continuing our example, identify the hypothesis test as two-tailed, left-tailed, or right-tailed. Since it is shaded to the right of 1.881, the test is right-tailed because the alternative hypothesis is of the form mu greater than mu sub 0. Example. The graph below portrays the decision criterion for a hypothesis test for a population mean mu. The null hypothesis for the test is H sub 0 equals, again, is H sub 0 colon mu equals mu sub 0. The curve in the graph is the normal curve for the test statistic under the assumption that the null hypothesis is true. For our graph, we have two z-scores, negative 1.227 and positive 1.227. The area to the left of negative 1.227 is shaded and labeled 0.055. The area to the right of positive 1.227 is shaded and labeled 0.055. Determine the rejection region. The rejection region is based on our z-scores and the shading of our area. Since the area to the left of negative 1.227 is shaded and the area to the right of positive 1.227 is shaded, z is less than or equal to negative 1.227 or z is greater than 1.227. Determine the non-rejection region. The non-rejection region is going to be between our two z values. So our z is going to be between the two numbers. Negative 1.227 is less than z, which is less than 1.227. Continuing with our example, determine the critical value or values. Our z-scores are the cutoff points between the rejection region and the non-rejection region. So the critical values are z equals negative 1.227 and positive 1.227. Determine the significance level. We have two areas. One is at the one to the left is 0.055. The one to the right is 0.055. So alpha will equal 0.055 plus 0.055, which is 0.11. Another way to find this number is to take one of our areas and just multiply it again. Another method to find alpha is to take one of our areas and multiply it by 2. Construct a graph that depicts your results. So we want to label where the critical values are. They are at negative 1.227 and positive 1.227. Then we want to label our rejection region. Our rejection region is to the left of negative 1.227 and to the right of positive 1.227. Our non-rejection region is between the two numbers. Continuing with our example, identify the hypothesis test. Continuing our example, identify the hypothesis test as two-tailed, left-tailed, or right-tailed. Since we have an area shaded to the left of a z-score and to the right of a z-score, the test is two-tailed because the alternate hypothesis, the test is two-tailed because the alternate hypothesis is of the form mu does not equal mu sub 0. Example, determine the critical value or values for a one-mean z-test. Draw a graph that illustrates your answer. a left-tailed test with alpha equals 0.05. First, we want to draw a normal distribution that is shaded to the left. Our alpha would be that area to the left, and negative z sub alpha would be the z value. Again, would be the z value. So my first step is to find z sub 0.05. Example. Determine the critical value or values for a one-mean t-test. Draw a graph that illustrates your answer. A left-tailed test with alpha equals 0.05. So let's start with what a left-tailed test would look like. We would have negative z sub alpha as our critical value, and alpha would be shaded to the left. The rejection region would be to the left of negative z sub alpha, and do not reject would be to the right. So let's change this drawing to reflect our example. First thing we want to do is label what we know. Well, we know that alpha is negative. Again, we know that alpha is 0.05 since the normal distribution adds up to 1. Okay, just starting over. Example, determine the critical value for a one-mean z-test. Draw a graph that illustrates your answer. A left-tailed test with alpha equals 0.05. For a left-tailed test, we have negative z sub alpha to the left of 0. Alpha is the shaded area to the left of our critical value. The rejection region is to the left of negative z sub alpha, and the do not reject region is to the right of negative z sub alpha. First, let's change our drawing to something that matches our example. What we are given in the problem is alpha, which is the area to the left of our z-score, 0.05. Since our normal curve adds up to 1, we know the area to the right is 0.95. Now we want to find negative z sub 0.05. Because z sub alpha always reflects the region to the right, when we want to calculate this, we need to type in 1 minus point again. Start again. We're ready to go to our calculator. Second, distribute. We want inverse norm, which is number 3. Since z sub alpha is always the shading, always represents the shading to the right, we want to type in 1 minus 0.05. We want to keep our mean 0 and our standard deviation 1, which is the default. Enter, and we get 1.6448. This rounds to 1.645. Since I have a negative in front of my z, I also put a negative in front of my answer. which gives me a critical value of again, since I have a negative in front of my z sub alpha, again, since I have a negative in front of my z sub 0.05, I also put a negative in front of 1.645. What you also may have noticed, returning to our calculator, returning to our calculator, second, distribute, number 3, inverse norm, I type in 0.05, enter, and I get negative 1.645. Since it is symmetric, I could use my definition of 1 minus alpha to find my z-score, or I can use alpha to find the z-score. Example, determine the critical value, again, determine the critical values for a one mean z-test. Draw a graph that illustrates your answer. A two-tailed test with alpha equals 0.05. Let's start with what a two-tailed test would look like. I have two rejection regions. My alpha is split up. Again, my alpha is split in half because half of my area is to the left of negative z sub alpha divided by 2, and the other half of my area is to the right of z sub alpha divided by 2. To begin, let's change this drawing to reflect our data. Again, to reflect our example. My shaded area is half of alpha. 0.05 divided by 2 gives me 0.025 on the left and on the right. That, again, which means I have 0.95 in the middle. I have z sub 0.025. Going to my calculator. Using the definition, I'm going to just click second, enter to retype, and then I'm going to change my 0.05 from my previous problem to 0.025. Second, delete allows me to insert my 2, enter, and I get positive 1.96. Since I need a negative and a positive z, I have negative 1.96 and positive 1.96. Again, going to my calculator, it is symmetric. Second, enter, I can type in 0.025, enter, and I get negative 1.96, which again leads me to my answer of a negative 1.96 and a positive 1.96. Example, determine the critical value for a one mean z-test. Draw a graph that illustrates your answer. A right-tailed a right-tailed test with alpha equals 0.03. A right-tailed test has an illustration where z sub alpha is positive and alpha is shaded to the right of z. Drawing this to match our data set, my shaded region is 0.03, which means my non-shaded region is 0.97. So the rejection my rejection region is 0.03 and my non-rejection region is 0.97. I want to find z sub 0.03. So doing this, again, go to our calculator. If I follow the definition, second, enter, I want to find 1 minus 0.03. Delete 3, enter, and I get 1.88. Also, using my calculator, since my normal distribution is symmetric, second, enter, I can just find inverse norm of 0.03, which is negative 1.88, and then change the sign because since it is right-tailed, I'm going to have a positive z value. Z sub 0 again, z sub 0.03 equals 1.88. Critical value approach to hypothesis testing. Rejection region. The set of values for the test statistic that leads to the rejection of the null hypothesis. Non-rejection region. The set of values for the test statistic that leads to non-rejection of the null hypothesis. Critical values. Value or values of the test statistic that separate the rejection and non-rejection regions. Obtaining critical values. The critical value must be chosen so that, if the null hypothesis is true, the probability of the two, the probability is alpha that the test statistic will fall in the rejection region. Critical values for a one-mean z-test at the significance level alpha. We have a two-tailed test where we have alpha divided by 2, since half of the area is to the left of negative z and half the area is to the right of positive z. Of a left-tailed test where alpha is to the left of negative z, and of a right-tailed test where alpha is to the right of z. To recap the section, critical values for a one-mean z-test at the significance level alpha. Step 1. State the null and alternative hypothesis. Step 2. Decide on the significance level alpha. Step 3. Compute the value of the test statistic. Step 4. Determine the critical values. Step 5. If the value of the test statistic falls in the rejection region, reject H sub 0. Otherwise, do not reject H sub 0. Step 6, interpret the results of the hypothesis test.